Any two from calculate a mean, reduces the effect of random errors, identify, remove anomalies. Yeah. Basically, when you're taking readings, every so often you screw up. The more readings you have, the more obvious the screw-ups are, and the easier it is to toss them away, the major screw-ups, and the more the minor errors you make average out to approximately correct. Random error because eye position will not be the same each time relative to the liquid. Allow a parallax error, but human error is insufficient. What error would be caused if this person did something wrong? A human error. No, that's not good enough. Parallax error, yes. Systematic error only if it is clear that the student always viewed liquid level from above or below rather than just from somewhere. Well, it isn't, so no. A temperature increase would increase the pressure in the tube even if the volume is constant, because a higher temperature would mean higher average kinetic energy of molecules/particles. Yeah, okay. More detail than I expected them to go into. An answer of 8 cubic centimetres scores 3 marks. I did say 8 cubic centimetres, didn't I? It's in proportion. Work is done on the air, so the temperature increases. That's pumping up the tyre. Work is done, that makes it hotter. Any three from, no carbon dioxide emitted. Just saying no carbon dioxide emitted when the question said shale gives off carbon dioxide, burning shale gas gives off carbon dioxide, doesn't cause global warming, that's a reason. Doesn't give off carbon dioxide, someone's just going to say, so what? Nuclear power doesn't cause earthquakes, indeed. More energy released per kilogram of fuel compared to shale gas, that is not a good enough reason in my opinion, because it's not taking into account how hard it is to get a kilogram of fuel to the power plant. What does it cost? How much energy do you burn up, do you use, getting a kilogram of fuel from the ground, in whatever form it's in, to ready for use form in your power plant? Just more energy released per kilogram is a bit crap when you're not specifically worried about lifting this stuff to the top of Mount Everest before you can use it, or something like that. Uranium or plutonium? Ignore any numbers given. I don't care whether you say uranium-235, they just want uranium. This nucleus splits into a neutron is absorbed by a large nucleus. It has to be larger than oxygen to undergo fission. Oxygen is the low energy state for some reason. The nucleus splits into two smaller nuclei. It splits into fission products, nuclear fragments, not necessarily two. Releasing energy and gamma rays. Is it gamma rays? Does it have to release gamma rays to be undergoing fission? And 2 or 3 neutrons. Description in terms of only atoms negates first 2 marking points. Has to be specifically nuclear, not atomic. Okay. Risk of electric shock if someone touched the case. Allow risk of electrocution. For 1 mark. 11 amps. You actually get 2 marks out of 3 for 0.011 amps because you failed to convert from kilowatts to watts for your calculation. Wow. 30 times 14 joules divided by, yeah, 0.12 kilograms. Gets you all 5 marks. That was the coffee heating thing. They did indeed say that the energy is the power output times the number of seconds, that many joules, which is the mass times the heat capacity times the temperature change. So divide that number of joules by both them and you get the mass. What was after coffee? It was a mass of air moving past a wind turbine, wasn't it? 1.2 density of air is mass divided by volume. Therefore mass is density times volume, which is 27,600 kilograms, or 2.76 times 10 to the 4 kilograms. Allow 28 or 2.8. 28,000 or 2.8, obviously. It's halved, which decreases kinetic energy by a factor of 2. Wind speed is halved, decreasing kinetic energy by a factor of 4, so kinetic energy decreases by a factor of 8. Allow power output in place of kinetic energy throughout. 3 marks. 388,000 is 0.5 times 13,800 times v squared. This was calculating the speed of the wind when there was a particular output. Yeah. This is what I did. The power output is a half mass v squared. V squared is twice the energy over the mass, or it's the mass, sorry, the power. The mass divided by half. It's the power divided by half the mass, I should say. Square root of 56.2 is 7.5. An answer that rounds to 7.50 meters per second scores 3 marks. I think I just got an A star, as they used to call them. Next paper. There's a paper 2. I don't know whether it's meant to be hard or just different questions for the same people the same year. So the same thing about higher tier. A child drops a ball. No funny comments, please. The ball hits the ground and bounces. Figure 1 shows the velocity time graph for the ball from when the ball is dropped until the ball reaches the top of its first bounce. Air resistance has been ignored. Yet the cyclist had 0 friction on a 100% efficient bicycle, but he was fighting air resistance. This ball has a less than 100% efficient bounce, I hope, but it has to deal with air resistance. Just ignore some of it, you know. Velocity is increasing, therefore this is the downward velocity, and then it suddenly becomes a negative number because suddenly it's going upward. And by the looks of things, that was an instantaneous bounce. This ball is made out of something very hard. And then velocity again increases to 0 when it's at the top of its first bounce and it is not moving up or down. Motion of the ball between points A and B, from here to here. It's in free fall. It says drops, so it's not going to be parabolic, it's going to be vertically straight down unless the child was moving at the time or riding on the back of a bicycle or something. 2 marks. If it was moving laterally, it will continue to do so at constant velocity and in the same direction. Meanwhile, accelerating downwards at we have 6 and 0.6, so this is exactly 10 meters per second per second. What direction is the ball moving between points C and D? Up. The thing is, velocity has a direction, you know, you could say velocity 0, here and here, at A and D, it must have been completely stationary, the child wasn't moving, but velocity has direction. If this is the downward velocity, which I presume it is from these straight lines, then horizontal velocity is just not factored into that graph. The ball and the earth form a system. What is meant by a system? It's a person with several different personalities. No, sorry, wrong field of study. A group of objects that interact. Yep. Objects with big differences in mass. Nope. Objects with gravitational potential energy. That's everything. So no. When the ball hits the ground, energy is transferred from the ball to the earth. Explain how the data in figure 1 show this energy transfer. Alright. When it hits the ground is at point B, when it leaves the ground is at point C, which is the exact same moment in time because simplified. But here you have it doing 6.5 meters, sorry, no, this is 6 to 8, not 6 to 7, this is 7 meters per second at 0.7 seconds, yes. 0.7, 1 meter. This child dropped the ball from 1 meter, okay. Ish, 0.495, nearly the same thing. 7 meters per second. When it came back up, it was only doing 5 meters per second. Alright, so the ball has lost 2 meters per second of velocity. It's gone from a half its mass times 49 to a half its mass times 25 joules of kinetic energy. The rest of it has gone, oh, excuse me, sorry, gone somewhere else. From the ball to the Earth, well, it's... Geez. To some extent, the Earth was moving towards the ball, and after impact, the Earth was moving away from the ball, but I suspect the actual loss of energy would really go to heat from a less than 100% efficient bounce. It heats the Earth at the point where it hit. If you don't believe me, you want to try picking up a freshly shot bullet. Or just driving a wood screw into wood, fresh wood, not an old hole, driving it back out and then grabbing it. It will be unpleasantly hot. Next question. A student carried out an investigation to, oh, of course there's sound as well. Did they negate air resistance? So maybe this child's operating in a vacuum and there was no sound. A student carried out an investigation to determine the spring constant of a spring. Table 1 gives the data. Force in newtons, extension in centimetres. Hang the spring off a thing, hang weights off the bottom of it. Well, the thing you use to hang the weights on ain't necessarily constant. Has weight of its own. Your weights aren't necessarily perfectly weighed. You have to hang a ruler down next to it, and you can't necessarily measure it accurately by eye. Might introduce parallax errors, as in other paper. If your ruler and your spring are hanging from an arm sticking out from a frame standing on a desk, that arm may be bending downwards, which means the top of the ruler will be getting slightly lower with each additional bit of weight. Six marks. And of course there's always the limit of proportionality of the spring. Rather than just the extension for one force suggests why. Well, as in previous paper, the more results you measure, the more your occasional errors average out, the easier it is to spot the fuck-ups, and if we want the spring constant, we want the coefficient of elasticity, we want to know the percentage extension of length for force, for a given force, per newton of force, or the amount of force required to double its length. And if this is all the data we're going to get, if we're not going to get the actual resting length of the spring, we need more than one force. What you could do here is say that 4 additional newtons from 6 up to 10 give an additional extension of 7.5 centimeters. Why is this guy only taking readings to the nearest 5 millimeters? Amateur! 7.5 mil, whereas from 0 to 4 you've got 7.5 centimeters. 8 centimeters. This is crappy measurement. It's approximately 2 centimeters per newton. A couple of these are slightly off. Actually, you can't work out the coefficient of elasticity there because you don't know the length of the spring. Never mind, my bad. It's just to, it's purely to average out errors. I was thinking of a different thing where you can actually determine a base value from a rate of change, but Complete figure 2 by plotting the missing data. Put a 2, 3.5 down there, and an 8, 12. No, 6.5. 8, 16. 8, 16. They're just going to want two x's added into the thing. Draw the line of best fit. Yeah, 8, 16. It's just going to be a straight line, just right at the middle. One of those each side. Tension, force, and spring constant. Anybody want to convert what I already said? Extension equals length times base length times force times spring constant. Apparently it isn't, because they're asking us to calculate and they haven't told us the base length, resting length. So it must just be extension equals force times spring constant. And we already know, oh look at that. That's per meter, not per centimeter, so it's not 0.5 newtons per centimeter, it's 50 newtons per meter. Proportional to the force applied, provided the limit of proportionality is not exceeded. Explain why the data supports the conclusion that obeyed Hooke's law. Because those points on that graph right there are in a straight line. And it has linear scales on the axes. Next question. P waves and S waves, yes! Proof of globe Earth right there. Are two types of seismic wave caused by earthquakes. Which one of the two of the statements is correct? Transverse, longitudinal, the last one. P waves longitudinal and S waves are transverse. P for push and pull, longitudinal, S for sideways, transverse. It's actually primary and secondary. P waves are effectively sound travelling through rock. S waves are what you get if you hold one end of a stretched out slinky and wave it side to side. Seismometers on the Earth's surface record the vibrations caused by seismic waves. Here we go, one P wave, bong. Calculate the frequency of the P wave shown in figure 3. Very conveniently, we've got passing up through the rest position there. 1, 2, 3, 4 times in 10 seconds. So the period is 2.5 seconds, so the frequency is 0.4 hertz. Simple stuff. Write down the equation which links frequency, wavelength, and wave speed. Wave speed equals frequency times wavelength. Travelling at 7,200 meters per second is the P wave shown in figure 3, that one that we just already saw. Calculate the wavelength. Well, we know the frequency is 0.4 because it went 10 seconds and it went 4 times, so it's once in 2.5 seconds, so it's 0.4 times in 1 second. 1, 2, 3, 4 times in 10 seconds, 0.4 times in 1 second. Duh. So we know the frequency here is 0.4, and we now know the speed. So 7,200 equals 0.4 times wavelength. 7,200 divided by 0.4 is 5/2 times 7,200, which is 5 times 3,600, which is 18,000. There. 18,000 meters. It's an 18-kilometer wavelength. Explain why the study of seismic waves provides evidence for the structure of the Earth's core. Told you there'd be a globe proof. This is the S-wave shadow zone. The P waves are effectively sound waves. Sound can travel through gas, liquid, and solid. Possibly also through plasma. I'd have to look that one up. Can't see any reason why it wouldn't. Right? So when it goes from solid to liquid, all it does is change speed. A P wave going down to the Earth at an angle, as the pressure of all the weight outside is compressing the rock harder and harder, the density increases and the P wave speeds up, so it gets refracted upwards. So if it goes down at a shallow angle, it'll go down, get refracted up and come back to the surface. Same applies to S waves. Where they go from a solid to a liquid interface, the P waves, going from solid to liquid, they slow down. The speed of sound through rock is a lot faster than the speed of sound in a liquid. So it slows down, it gets refracted down through the liquid inner mantle and outer core. When an S wave gets to there, it can't conduct from solid into liquid. You imagine putting your hand down into one end of a swimming pool and waving it from side to side, you're not going to produce side to side waves at the other end of the swimming pool. But if you make a very loud bang underwater in a swimming pool, that sound will transmit through. So what we get on the surface of the Earth, all these seismometers everywhere, is the P waves showing up. The P waves and the S waves showing up in the area around the earthquake, and quite a long way around the Earth from it, up to the point where the waves that hit the solid to liquid interface. Come on, I want a bigger image than that. This one will do. Will it? No. Huge image wanted. None of these images is huge. I want a huge image. Screw it. Up to the point where the waves that just missed the solid to liquid interface, up on the left and right shoulders in this diagram, are coming to the surface. So these are your waves, P waves and S waves. Oh, this one doesn't show the S waves. That's annoying. Getting refracted back up. And because we don't have S waves in that diagram, I'm going to grab one that does, assuming I can find one that does. Normally there is one that does. Apparently we don't have one that shows... Oh, there's one that does. Right. Have an earthquake happening somewhere near the surface at the top here. They've marked epicenter, they haven't marked focus. So the earthquake actually happens at the focus, the epicenter is the point on the surface above it. But whatever. P waves and S waves get refracted upwards to the surface up to here. This far around the Earth, 105 degrees around the Earth, in all directions, you can pick up both. But where this solid to liquid crossover happens, the S waves can't get through. These black arrows indicate paths of S waves that hit this and just disappear, dissipate into the liquid. Whereas the P waves do get in, but they get refracted down. The pale yellow lines coming out here and then refracted sharply down can come through and miss the solid inner core, so it's just got this smooth, again refracted upwards path, and then it gets refracted down again, coming from liquid to solid as it comes out, and then refracted up on the rest of the path. So you get here a P wave that has gone through solid, through liquid, through solid, and it gets detected again, 140 degrees around. There's this gap here, and of course here, and across the front and back of the diagram. In the middle, these P waves are getting refracted down and hitting the solid inner core, where they accelerate, which causes them to be refracted. Why is it showing them refracted down again? Kind of weird. I would have thought they'd refract up. Apparently that slows them down. That's very bizarre. According to this diagram, they are slowed down in the solid inner core. But it's acting as a lens, focusing them into this area where they get refracted back down. It's the same kink as you see there. So out here you're getting the P waves once, but at a different time from where you'd expect based on all of these P waves and angles. And here in the middle you're actually getting P waves that came through the solid core, so you get a different time again. All the way across here, no S waves. That's why. Explain that whatever you like. Because the Earth is roughly spherical, they probably treat it as perfectly spherical in this paper. We get earthquakes all along the fault lines and occasionally off them, all over the Earth, and they get detected all over the Earth if they're big enough. And no matter where the earthquake happens, you get the same shadow band here, where there's no P waves, and this whole area where there are no S waves. It's always the same size and shape, meaning that the Earth's inner core is always the same size and shape, which for 2 marks on a GCSE paper is probably excess information. The fact that it's very slightly lopsided because the core isn't perfectly spherical, and of course the Earth is actually an oblate spheroid, not a sphere, and it has longitudinal asymmetry and it's kind of lumpy. Yeah, never mind that. Figure 4 shows a simple seismometer made by a student. I'm glad it was made by a student, and I'm really glad we know it was made by a student. Heavy base on the floor, data logger computer, coil of insulated wire, bar magnet, spring. Right, what's happening here is a bar magnet is suspended above a spring. I'm sorry you can't see that because I forgot to zoom back out. There we go. A bar magnet is suspended above a spring which is connected to a data logger which is connected to a computer. The spring is mounted on a heavy base on the floor, but the coil is mounted on a heavy base on the floor. The bar magnet is suspended from a spring mounted on this arm up here. So if an earthquake bounces the floor up and down, the computer, the data logger, the heavy base, and the coil will bounce up and down, but with this spring acting as a shock absorber, the magnet is going to stay still, which from the point of view of an observer bouncing up and down with the floor will make it appear that the magnet is bouncing up and down. It is, relative to everything else in the room. Magnet passing through coil of insulated wire generates current which can be detected and logged by the data logger. And I clicked in the wrong place. The arrow button to scroll down gently is kind of small. Why does the movement of the bar magnet induce a potential difference across the coil? Because you're moving a magnet past a conductor. Dynamo effect happens. I think it's left-hand grip rule for dynamo. Why is the induced potential difference across the coil alternating? Because the magnet is bouncing up and down, not just passing through in one direction. Boing. There you go. The description of this is boing. Which statement describes the movement of the magnet when the induced potential difference is 0? Stationary. Seismometer cannot detect small vibrations. Suggests 2 changes to the design that would make it more sensitive. More powerful magnet and more coils of wire, because the more coils of wire there are, you have the more current will get generated by the same movement. Because yes, another change, which is to add things that will detect movement in the other 2 axes rather than just the vertical, but hey. Figure 6 shows an unusually shaped container. Oh god, the fluffs are going to love this. The container has 4 vertical tubes of different shape and size. Vertical? The container has 4 vertical tubes of different shape and size. I'm sorry, but tube 2 doesn't look very vertical to me. Now there's 3. It's got a bit of a rightward trend as well. Water is poured into the container up to the level shown in tube 1. Complete figure 6 to show the height of the water in tubes 2, 3 and 4. 1 mark. I'm going to assume this thing isn't big enough for Earth's curvature across its width to have a measurable effect. Just assume it's drawn life size, and it's